My name is Alana, and I'll be presenting different data analysis that you can do inside of SAS-JMP. So this is an overview of everything that I'm going to be going over. It's 10 different data analysis that you can do inside of JMP. So for each one, I'll give a brief synopsis of what it is, and then go into JMP and give a demonstration of how to use it. So for this first one, the Graph Builder, it's basically an interactive tool that you can use to analyze data. And a good reason for using this would be if you're not really sure what type of graph you need for the data set that you have, you can use this to get a better understanding of how you should be modeling the data. And the data set that I'm going to be using is crime, which is a sample set already established inside of the JMP software. So as you can see with this crime data, the first column is of each of the 50 states, and then you have different crime types like murder, rape, robbery, and so on and so forth. And it gives different numbers for those. So first you click on Graph, and then you click on Graph Builder. So here our focal point is going to be of the state, so we're going to drag that to the center. And as you can see here, it's giving you a map of what it's supposed to be doing, and up here you can see what it's clicked on. It's clicked on this first one, and it's called Map Shapes. And if you hover over each one of these, it gives you a brief understanding of like what each one is and what it does. So for this map shape, it shows areas defined by a map shape variable, usually with a color variable. So that color variable comes in with one of these different crime types. So I'm going to click and drag murder and put it in this color column right here, and it shows the different colors. So as you can see, the higher murder rate is the darker red, and you can see it right here in Nevada. So another thing that you can look at is all of these different types of summaries. So if I would change it to something like percent of total, it changes these numbers over here to the side. But a better model for this one would be the mean, so we're just going to leave it on mean. And that's it for Graph Builder. So now going into bivariate analysis, this is showing the relationship between two continuous variables. And it gives a scatter plot, which is shown down here in the corner. That's a result from a data set that you can have. And you can put different types of lines in this. I'll show a little bit more of that inside of JMP. So the data set that we're going to be using is SAT. So here's the data set here, and the SAT data set is basically giving all 50 states and is splitting them into two different areas, which would be verbal and math, as you can see here, and it goes over different years. So what we're going to click on to do this analysis is analyze and then fit Y by X. So the thing that we want to be testing, that I wanted to test here, was basically the relation between the percent of people taking the SAT in 2004 versus the verbal test scores of 2004. So we're going to put the percent of people taking it in the X for the factor, and the test scores for the verbal portion of the test in the Y response. So as you can see here, there's blue triangles beside both of these, so they're both continuous variables. So as you can see down here, for a continuous Y variable and a continuous X variable, you're going to get a bivariate graph or model. So I'm going to click OK, and as you can see, again, that scatter plot shows up, and I'm going to click this red triangle here, and we're going to first click fit mean. So it gives this straight line here. I'm going to click this little arrow here, and this basically gives you the mean of whatever is in your Y or your response variable. And that's what we put here, which is the 2004 verbal. So that's the test scores for that verbal portion of the test. And then I'm going to click the red arrow again, and this time I'm going to click fit line. So this gives a line of best fit. and it gives you a whole bunch of different data for this. And the main thing that I wanted to be looking at here was the p-value that was given. And since this p-value is less than 0.05, then we can say that there is some significance with the data. So for this particular model, we want to say that our null hypothesis is that there's no difference between the two things that we're comparing, which would be the percent of people taking the test in 2004 versus the verbal test scores. So again, there is significance, so there is a difference in this data. Now going into the ANOVA test, which means the analysis of variance, we are looking at the distribution between a continuous y variable and a categorical x variable. Inside of JMP, categorical can be classified as two different things, and that would be nominal or ordinal. And the results that would appear is a plot, and that's given right here in this corner, and we're going to be using the data set called analgesics inside of JMP. So here you can see the different things that are in the data set. So the gender of the patient, the drug that they're given, which is A, B, or C, and the pain level. So basically with this data set, 33 patients are given one of the three different types of drugs, so A, B, or C, and they are asked to rate their level of pain, and that's what these numbers are right here. So we're going to click on Analyze. Again, we're going to click on Fit Y by X. And for this one, we want to look at the significance between the type of drug the patient uses and the amount of pain that the patient is experiencing. So we're going to put the drug inside of the X factor, and then pain inside of the Y. So the reason I did it this way is because to get a one-way ANOVA test, which is what we're looking for, we want the continuous variable to be in the Y column right here, and then the categorical to be in the X, and that's what I did here. So I'm going to click OK, and this plot shows up, and we're going to click this red triangle and click on means/ANOVA, and you can see these green diamonds show up. So basically these diamonds are giving a confidence interval of each of the drugs. So this middle line here is the mean of each one. So this is the mean of drug A, this is the mean of drug B, and this is the mean of drug C. So we can see that for drug A, this diamond is squished a bit more than these two, and we can say that this one has less variance, and you can actually determine that by going down further and looking at these different values that are given. So one thing that we want to look at is this p-value again, and it is below 0.05, so there is a significance in the difference between the different drugs that are used. So again, this would be a null hypothesis that there's no difference between the drugs, but this p-value is stating that there is a difference. This is the chi-squared test. So for this one particularly, we're looking at contingency analysis. And this is where you have two different categorical variables. And again, categorical inside of JMP would be nominal or ordinal variable types. And the result for this would be a mosaic plot and a contingency table as well. And the data that I'm going to be looking at is carpool. So this data here is giving three different variables that are looking at specifically the owner of the vehicle. So if they are male or female, their marital status, and their age. And then these three right here are about the actual car. So the country of origin of the car, the size of the car, and the type of car. So we're going to click on Analyze and then Fit Y by X. And we're going to be looking at the size versus the country that the car was made in. So we're going to click country and put that in the X, and the size and put that in the Y. So again, we're going to look down here. So for a contingency plot or analysis, we would need two different categorical, like I stated earlier, and the categorical that we're using are nominal. So these red ones are nominal, but the green are ordinal. But we're using two different reds. So I'm going to click OK. And this mosaic plot shows up, and it's showing these different blocks. So as you can see here, this one is really tiny, and it's showing that there are very few Japanese cars that are large. So we're going to go to this contingency table, and this is giving actual numbers for what you see in this mosaic plot. So right here, for example, a car made in America and that is large, there are 36 of those. So that would be this area right here, American, and then in this large area right here. So that's that 36 right there. So we're going to scroll down a little bit further, and we can see this is chi-squared because it says it right there. And we're going to look at the p-value for this chi-squared test. So it is below 0.05 again. And the chi-squared null hypothesis is different from the ANOVA in the sense that for chi-squared, it would be that there is independence between the two things that you're testing. So in our case, our null hypothesis would be that there is independence between the country that the car is made in and the size. But since there is significance, that means that both of these variables are dependent of one another. So now with the design of experiments, or the DOE, this is for increase in productivity and improving the quality of a product. So this is analyzing different trials that you could use mathematically instead of doing a whole bunch of physical trials and wasting money and time. You can do it mathematically and get a better understanding of what you need to improve on. I'll give a better understanding of this inside of JMP, but it's a good model for analyzing the profiler function, and in JMP we're going to be using the popcorn DOE results. So here's the data set. It's the different brands, so we have two different brands, Top Secret and Wilbur, and we have different times for those, and the power setting, I guess, of the microwave, and then the number of kernels popped of the popcorn, and these are the total kernels inside of the bag. So we're going to click on DOE and evaluate design. And from here we're going to have brand, time, and power inside of the X, or the factor. And we're going to do that by the number of popped kernels. I'm going to click OK. And then this shows up with the different combinations that you can have that they did inside of it. And I'm going to scroll a little bit further. And again, with that profiler that I was talking about, I'm going to click this arrow to expand this. So you can see here as the Top Secret is one of the better choices with a time of 4 and a power of 7.5. So this variance is at 6.8. We want it to be closer to 1. So I'm going to click this red arrow and click maximize desirability, and you see you get different results. So it's still the Top Secret brand, but this time we have a time of 3 instead of 4 and a power of 10. And the variance is much closer to 1 now. So this is a better model. So now looking at the hypothesis test, this is just testing a theory that you've come up with and seeing whether it's credible or not. And inside of JMP there's 4 different types of hypothesis test. We have the 1 means, the 2 means, 1 proportion, and 2 proportion test. And in JMP we're going to be using binge data. So this is the data set here, and as you can see there's a binge frequency column right here. So people are drinking at least once a week, at least once a month, at least once a year, or never. And then it's saying whether they got into an accident because of this, and then you have the number of respondents for each. So going into this help tab here, and then clicking on sample data, you can see a whole bunch of tabs show up. This is where I get most of my sample data at. So scroll down, and then you see these calculators. And as I said before, there's these 4 different hypothesis tests. 1 means 1 proportion, 2 means and 2 proportion. So we're going to click on 1 proportion, and we're going to click on summary statistics. Okay. So what I wanted to find out is whether it's valid to say that 10% of the population are binge drinking at least once a week. So based on that question, we want to use a two-tail test. And the hypothesized proportion is, again, 10%, so you say 0.1, and then the number of successes, so that's the number of people drinking once a week. So you have to look over here in the data and see how much that is. So we have respondents, we have 415 plus 70, so we have 485 for the number of successes. And then the sample size will be the total of all of the respondents together. So I've already added that up, and it's 3,801. And then normally for the significance level, we want to have 0.05. So I'm going to go ahead and type that in. And then this pops up. So you can see that the number of successes of this is 13%. So to get a better understanding, this is a great tool to use. This little checkbox here says reveal decision. So it says reject null hypothesis. So therefore we can say that it's not valid to say that 10% of the population are drinking at least once every week. So now with control charts, this is providing feedback on specific variables that you're looking at to show if the process is statistically in or out of control. So some common control charts that we can look at is the X bar, meaning average chart, the R chart, which is range, the P chart, which is proportion, the C chart, which is count, and the S chart, which is sigma. So sigma, that is meaning the variance of whatever product you're using, so how much variability you have in producing that particular product. It's similar to the R chart as well, because the R chart is taking the highest value and the lowest value and subtracting and seeing how much variability, again, you're having in your data set. And with the P and the C chart, they are similar in the sense that they are looking at the amount of defects. So with the count chart, it's giving actual numbers of how many defects you have, whereas the proportion is giving you a percentage of the of how much you're defecting. So in JMP, we're going to be using diameter. Go over here. So this is the data set. You have the specific date of creating the product, and then the diameter of the product, and the operator, and then the machine that it was created on, and whatever phase it was in. So it's only 2 phases in this data set. It's 1 and 2. So I'm going to click on Analyze, and then go down here to Quality and Process, and then Control Chart. So the one I want to look at is X bar, but again, you have different charts that you can look at, C chart, P chart that I explained earlier. So I'm going to click on X bar chart, and as you can see here, it's checked on 2 different things, so the X bar chart and the R chart. So we're looking at the average and the range. So I want to click on diameter to put that as a process, and then the day, that's how I want to label the x-axis. And then we're also just going to put phase into this phase right here. So I'm going to click OK. And a reasoning for using an X bar and a R chart together, the X bar chart is just giving an average, and if a data set is oscillating back and forth over these control lines, you're going to have an average of a good number because it's going back and forth to different extremes. But this R chart is showing you how much variability is actually in your data set. So those are needed together. So right here you can see that there are 2 points in the X bar chart that are going over this line right here. This line is the control limit. So how much you're able to produce, or how well you're able to produce it. So I'm going to click on this red arrow and then go down here to these different rules that you can check for, and it tells you if there could be potentially a problem with the process going out of control with each point, and it gives you these numbers. Yeah, you can search further into different rules and how to determine whether something is in or out of control. For this process, you can see that these 2 points, after this particular point, the process does go back in control. So the model is fine. So now with Pareto chart, this chart shows the frequency of problems in a process or operation. It helps the business to know where they need to focus their efforts. So when talking about the Pareto chart, you have to talk about the rule of 80-20, which is stating that 80% of your consequences or failures comes from only about 20% of your causes. So in JMP, we're going to be using failure. So here's the data set. This failure is supposed to be of different circuits that you're looking at. So these would be the failures of certain circuits. And this will be the frequency of them. So I'm going to go to Analyze, and then Quality and Process, and then Pareto chart. So in here we want to put failure into the Y, or the cause, and the N into the frequency, so how many times that's coming up. And I'm going to click OK. And then this chart shows up. This is the Pareto chart. So this line right here is an accumulation of these different bars. And these different bars represent the failures. So right here you see corrosion as one of the failures or reasons for failure. So like I said before, 80% of your failures are happening in only 20% of your causes, and these are the causes. So another thing you can look at with a Pareto chart is a pie chart. So all you do is click on this red arrow and then click pie chart, and they give you a pie chart here. You can also study that as well. So now looking at reliability and survival, there's a lot of different things you can click on inside of JMP, and these are those different things that you can look at. So I'm going to give a brief synopsis of what each one of these are. So the first one is the life distribution, and this one helps discover distributional properties of time to event or time to failure data sets that you can have. And then the next one we have fit life by X, which is closely similar to fit Y by X, but instead of using any Y variable, you would be using a life or a time series variable, and it helps you analyze lifetime events when there's only one factor presented. And then we have recurrence analysis, and this one is, for example, if you're using a particular piece of machinery, you want to see how often a particular failure occurs with that one piece of machinery. I'll go a little bit more into depth about this when I'm doing the demonstration, and I'm going to be using bladder cancer data. The next one is degradation, and this one is used to predict pseudo failure times. And then we see reliability forecast, and this helps predict the number of future failures that you might have. It's great for looking at warranties, so a company can see the time frame of when a product is going to fail so they can reduce the amount of warranty claims that they would have. And then we have survival. So this is using a single Y variable that represents the time to event or time to failure, and this analysis is used to examine the distribution of failure times. Then we have the fit proportional hazards. Normally when you're looking at a continuous distribution, you want to look at a specific time of when there's a failure, but with continuous data you can never get that specific point because it's always going to be very, very small, so it's going to reduce it to be 0. And hazard looks at a specific interval and allows you to get as close as you can to that specific time of when the product is failing. So now going into JMP, again, I said I was going to use the bladder cancer data, and this one is for the recurrence analysis. So there's different patients, and then they're giving different drugs or treatments, and then this is the occurrence of their tumors and so on and so forth. So I'm going to click Analyze, and then I'm going to go to Reliability and Survival, and then Recurrence Analysis. And in here, I just wanted to put in the Y column, I needed age, so I'm going to drag that over here. And then the ID would be the patient number. And then we're going to put cost into the cost. This isn't an actual pricing of how much, I guess, the tumor would be. It's actually saying that there was a tumor or there wasn't a reoccurrence of a tumor. And then we're going to look at grouping, and we're going to put in treatment group for that. I'm going to click OK. And then you see this event plot right here. The main thing we're going to focus on today is this MCF plot. MCF stands for the mean cumulative function, and it's telling you how many times it's going to reoccur. So right here you can see a MCF of 2. So that's saying that it's going to occur twice at whatever age that you're at. So this age, I'm assuming that this is the amount of months after the removal of the bladder cancer. So right here you can see the different drugs, so the different colors. You have the red is a placebo. I'm not really sure how to pronounce these, but the green is the pyridoxine, and then the blue is the thiotepa. And so for the MCF of 2, you can see that that's around 35 in age for the placebo and the pyridoxine. So we can see that this blue one, the thiotepa, is the best option for drugs that you would want to choose. Last but not least, we have the time series model. So time series data is commonly used to predict patterns, and it allows you to forecast out future periods. So the main thing that we would be looking at when we're looking at time series data is if the data has different trends or seasonality in it. We want it to be stationary and for it to be white noise. So having different trends in there would skew the data, because we can mathematically format these trends or seasonalities. And we just need to see where there is more variability or where we can't really predict. We want to look at that particular part of the data. So in JMP, I'm going to be using India Industrial Production data set. So here's the data set, and we're going to be using month as, like, this is our time frame that we're using, and we're going to be using basic goods. So I'm going to click on Analyze, Modeling, and then Time Series, and we're going to put basic goods as our Y and months as our time ID. And you can change this right here to have different amounts of your sample size. So we're going to do a lag of 25. We're just going to go out 25 periods. I'm going to click OK. And you can see that you have this confidence interval here, and same here. So for this one, this is the autocorrelation, and this one is based on a moving average model, and the partial autocorrelation is based on a autoregressive model. So we would want to have straight lines here. So I'm going to click this red arrow, and I'm going to click difference, and we're looking at non-seasonal data because there's just a trend upwards here. We want to get rid of that. So I'm going to go and try a difference of 1 and see what happens. So I'm going to scroll down. As you can see here, it's no trend going upwards now, and it's a little bit more straight, but it's still curving out. This model isn't the best that could be used, but it is showing some difference from the original, which definitely had a trend upwards. So now I'm going to click on this red arrow again, and then I'm going to click on ARIMA. I'm not going to click on seasonal ARIMA because, again, we're not working with seasonal data. And I'm going to click here and say 1 for our autoregressive order. And then, again, before we had put a difference of 1, so we need to remember to put that in there. I'm going to click on estimate. So right here you can see that this is checked right here in our report. So you have this AIC score. If we wanted to conduct different models, we would want to look at this AIC score to see which one is the lowest. The one with the lowest AIC is the best option. So I'm going to scroll down, and you can see right here that we have a forecast, and these are the confidence intervals of that forecast. So as you can see, this model isn't the best, but I would say to get a better understanding of a lot of different things that this time series data can do, look at my previous video. I'll have the link in the description. So thank you for watching another one of my videos.